Prelim of the physical science, so it's P.1, the Prelim of Gauteng. Okay, so we have 10 questions that we shall be looking at. So question number 1, they're telling us if we have an air bubble in a tank that is rising vertically at a constant velocity. Okay, so if the velocity is constant, which means we don't have any sort of acceleration. So the forces acting are given below. So X, Z, and Y. So if the bubble is rising, which means this force, the upward force, must be greater than these two combined. Okay, so they're asking us for the incorrect option. Okay, so option A, they're telling us that X is equal to Y plus Z. Okay, there's some bit of truth in that statement. And then B, for us to get Z, we have to get X plus Y. No, there's no truth there because it should be a minus, since these ones are acting in the opposite directions. Then for us to get Y, you shall get the X minus Z. That's okay. Telling us X is greater than Z. That's true, which is also greater than Y, which is also true. So since there is some bit of truth in A, we shall go with option B as our answer for the incorrect. Then if a person stands on a scale in a lift, the motion of the lift is given in terms of its acceleration, which situation represents weightlessness. And so we know that weightlessness is a scenario whereby an object or a person feels like a free body, where the only force that is acting on that object is the acceleration due to gravity. And we know that acceleration due to gravity will always act downwards, and the value is 9,8. So option A is off. Okay. We know that at a constant speed, the acceleration is a 0, but now the acceleration will always be 9,8 downwards. So I'm going to go with option C, whereby the acceleration, the downward acceleration will be 9,8 meters per second squared. Then 1.3, if a golf ball falls vertically downwards from rest in air and bounces back to the same height from which it was dropped. Okay. Which of the following scenarios are correct? So the first option you have is it experiences a maximum speed at the minimum height. This is very true, because for the object to get back to the same height, which means the speed at the point of bouncing should be greater. Okay. Then the displacement falling is equal to its displacement that is rising, since the height reached before and after is the same, which means that option is also correct. And then it experiences minimum speed at the maximum height. So we know that at maximum height, the V final is always 0, which statement is also correct. So the combination of the options that are correct, I'm going to go with option D, which is all the 3. Okay, then 1.4, if a ball of mass m moving the velocity v collides head-on elastically. Okay, so elastically means we're going to conserve momentum, and we're also going to conserve the kinetic energy. Okay, with another body of mass m moving at the same velocity v in the opposite direction, after collision, both bodies will move with a velocity v. That is true. Both bodies travel in opposite direction with a velocity v. This is a bit more detailed. The opposite direction and then a velocity v. I mean, it's a head-on collision. Okay, both bodies are going to go off with the same velocity. It's just more like they bump each other and then they move on in opposite directions. Okay, so both balls move at right angles. Nope. One ball comes off at rest and that's out. Okay, so I'm going to go with option B for 1.4 because it has more truth in it. And then 1.5, if a mass is lifted from rest in the ground to a point H, okay, P is the increase in the gravitational potential energy of the mass, and then K is the kinetic energy at mass H. Okay, the expression that is equal to the mechanical work done. So mechanical work is a combination of both the kinetic and then the gravitational potential. Okay, so which means I'll have my K and P added together, the combination with a plus, which is option A. We can't minus, we can't multiply. Okay, then what does the term redshift mean? 1.6, I'm gonna go with option, an object in space, no, the color of a distance somehow, the expansion of the universe. This makes more sense. Okay. Then 1.7, which of the following graphs has a slope that is equal to the Coulomb's constant? Okay, so we can see that the y-axis is having just the intensity, electric field. So if I'm to get the formula, which is E is equal to KQ divided by R squared. Okay, so if I make this the subject, if I make K the subject, it's going to be ER squared over Q, which could also be written as E over Q over R squared. That is our K. We know that it will be directly proportional. Okay, so all the graphs, like the shape is fine, but now what we need to check is basically the variables. So E over Q1, that is out. E against Q1 over R squared. This makes more sense. E over R squared, no. E Q over R, no. So C will make more sense. Then 1.8. 3 resistors are connected in a circuit. Then there is a 4th resistor that is connected parallel to the 4 ohm. Okay, so if we have another resistor that is connected in that format, if we had to compare the original circuit, compared to the original circuit, how will the power dissipated by the 8 ohm and the 4 ohm change? Okay, so initially, before we introduce this other resistor, the current that was flowing here, let's say, was maximum current. So 4 ohm was receiving the maximum current, and as much as the 8 ohm was getting split, okay, which was still a bigger share. Now, if we are to look at power, let's look at the formulas of power. We can use power is equal to IV, which is the same as I squared multiplied by R. Okay, so power is directly proportional to that, and okay. So if we introduce the 4 ohm resistor, what's going to happen is that the current that was initially in the circuit is going to be split up into 2. Okay, and then the fact that the current here is smaller than the original current, and we know that current is directly proportional to the power is going to decrease in the 4 ohm. Okay, so the same story happens to the 8 ohm and the 10 ohm, because this current that was split up must again be split up again for the second time, which means the power that is being received here is going to be way smaller. Okay, so even the power there is going to reduce as well. So decrease is option A that I'll go with. Then 1.9, an immersion heater can be operated either from an AC power supply or a DC. Graph represents the potential difference when the AC power supply is used. Okay. So if this is the AC, which means this is Vmax. Okay. What DC supply? So which means we must get the VRMS, which is Vmax divided by the square root of 2. So our Vmax is 12, so 12 over root 2. That would be the answer. Then 1.10, the work function of a metal is given as that. Then if this metal is illuminated with light of frequency 3f0, okay, 3f0, they want us to determine the kinetic energy. Not just kinetic energy, but the maximum kinetic energy. Okay, so we know from our formula page, okay, that E must be given as W0 plus EK max. Now we want the EK max. So our EK max should be the same as the energy minus the work function. But this energy is given as the HF, but we know that the F is 3F0. So which means this is going to be 3HF0 minus the work function, which is just HF0. Subtract that, we get twice HF0, which is option B that I'm taking. All right, then question 2, they want us to determine, a toy train of mass 2 kilograms. Okay, we have 2 kilograms there. And then there's a mass of 1 kilogram. are attached to one extensible string. The car train system is pulled through a rough slope at a constant velocity by a rope. That's T2 acting on the rope at 10 degrees. Okay. Then explain the term net force or resultant force. So we know that this is basically a single force. Okay, it's a single force that has the same effect. That has the same effect as all the individual forces. As all the individual forces that are acting on an object. So it's just one single vector force that has the same effect as all the forces that will be acting on that object. Then 2.2, they want us to draw a free body diagram of the toy train for 5 marks. So 5 marks will be like 5 forces, okay? So I'm gonna have this at an angle, which is a T2. Then I'm gonna have my FG parallel. I'm also gonna have my T1. I'm also gonna have my frictional force. Then I'm gonna have my weight. I'm gonna have my normal force. 1, 2, 3, 4, 5. We have 6 forces, but N5 would be better. Okay, then they're telling us that the tension T2 is 20 newtons, causing the system to accelerate up the slope. Calculate the magnitude of the acceleration of the system if the frictional force that is acting on the car is 1,5 newtons and that of the train is 2 newtons. Okay, so there are 2 ways of doing this. We can look at the train on its own, and then we also look at the car on its own, and then we solve the system simultaneously. And so if I look at the train, let me start with the train. Okay, so when we look at 2.3, they're asking us that the tension is increased to 20 newton, causing the system to accelerate up. Initially, it was just a T2, then it is increased to 20. Calculate the magnitude of the acceleration of the system if the frictional force acting is this and that. Okay, so what we're going to do, I'm going to look at the 2 bodies separately. One, I can start with the train. With the train, it's going to be, let me break this down to a T2 cos of 10, okay? So it's gonna be T2. Let me start with the formula and say F net is equal to MA. So T2 cos of 10 minus, I'm going to have the FG parallel there, which will give me the mg sine of theta minus the frictional force minus T1 must give us MA. Okay, so this is going to be 20 cos of 10 minus 2 times 9,8 sine of 20 minus the frictional force, which is a 2, minus T1 gives us 2A. Okay, so when I look at the left-hand side and what goes there, so it's 20 cos of 10 minus 2 times 9,8 sine of 20 minus the 2. I'm getting 10, let's see, 10,993. I'm subtracting T1 to give me a 2A. Let me make T1 the subject. So T1 is going to be 10,993 minus 2A. Call that equation 1. Then let me focus on the car for now and do the same thing. So we're saying F net is equal to MA. So looking at the car, this T is going to be upwards. There's going to be FG parallel and also the frictional force downwards. So it's going to be T1 minus the FG parallel minus the frictional force. I think that is it, is equal to MA. So our T1, we don't know what it is, minus the mg, which is 1 times 9,8 the sine of 20. We are subtracting the frictional force, which is 1,5, should give us just 1A. Let's simplify that. So T1 is going to be 9,8 sine of 20. Okay, I'm subtracting 1,5. This is going to give me, this is going to give me 1,852 plus A. Okay, this is what I'm getting for T1. Subtracted the gravitational. Okay, and then we've also subtracted the frictional force. All right, so let me try to equate the two equations and see what I end up with. Okay, so 10,992, that's 993. Okay, minus 2A should give me 1,85 plus A. I would do the transposition. Okay, so now I transpose that 10,993 minus 1,852. That gives me 9,141. Should give us 3A. Divide both sides by 3. Okay. Then I end up with 3,05 meters per second squared. All right, so that is what we're getting with 2.3. That's what we have with 2.3. Okay, so that is what I get if I use this approach, okay? But then if somebody uses the combined systems approach, I'm gonna get a different answer. I don't know why it gets to that. Okay, so if I look at the T2, which is 20 cos of 10 minus the combined gravitational forces, which is going to be 3 times 9,8 sine of 20 minus the combined frictional forces, which is a 3,5. This should give us the combined mass, which is 2 plus 1, which is 3A. If I use the combined everything. Okay, this gives me 6,1407 is equal to 3A. Divide both sides by 3. That gives me 2, something. So A is 2,05 meters per second squared. I don't know. That's what I'm getting. So 2.4, they're telling us that halfway up the slope, the string in T1 breaks and the car rolls down the slope. Does the friction of the train increase, decrease, or remain the same while moving up the slope? Explain the answer. Now, the fact that T2 is still constant, okay? The fact that T2 is still constant and it's pulling, this entire section is going off, which means the frictional force that is trying to pull the train downwards is going to decrease. Okay, so my option or my take will be decrease. Okay, so snapping of T1 will decrease the forces that act on the train down the slope. Okay, so the train is only going to be left with just the gravitational as well as the frictional force that it has. So the frictional here, the gravitational and the tension will be completely off. All right, so that is that with question 2. Question 3, they're telling us a tennis ball falls freely from rest from point A, which is 44 meters above the ground. And then the time taken to fall at different positions, B, C, D is given in terms of T as shown. So define the term free fall. So this is basically the motion of an object. Motion of an object. Free fall is motion of an object. in which the only force acting on it, only force acting on the object is the acceleration due to gravity, or just a g. Then 3.2, they want us to get the value of t. Okay, so for the value of t, what we can use the delta y formula and see this is v initial multiplied by t plus a half a delta t squared. So we have our delta y as 44. Initially, the ball was just dropped. So this is 0. So that falls away. We have a half. Our a is the g, which is 9,8. And then this is going to be, why should I use? Okay, let me just get the t from here now. Okay, so what I'm going to get is going to be 44 is equal to 9,8 divided by 2. That's going to be 4,90. This is squared. Okay, divide both sides by 4,9, and then a square root. So square root of 44 over 4,9. Let's see, 44 divided by 4,9. That's giving me 2,996, which is approximately at 3. Okay. But the question wants the value of t. Remember, the t that I got is the time that is taken for the object to reach the ground. So how many t's do we have here? There are basically 6 t's. So 6 t's will be equal to 3, then divide both sides by 6. So t becomes 0.5 seconds. Alternatively, the 6 could have been included at this point so that you get the 0.6 straight away. Okay. So that is how this would have been obtained. I don't know why I used this approach, but it is not making sense. But then the final answer has to be 0.5 seconds. Then calculate the height of the ball at point C. Now, since we know that for the ball to reach C, it's going to fall through 3 t's. Okay, so which means the time will be 3 times 0.5, which is 1.5. That's going to be 1.5 seconds. Then if we have the time as 1.5 seconds, our v initial is 0. We're looking for the displacement. We can still use the same formula. So delta y is equal to vi delta t plus a half a delta t squared. So this initial will die out, and then we shall be left with just a half times 9,8 multiplied by, we're saying this is 1.5 squared. Okay, so 1.5 squared, what are we going to get there? So 0.5 times 9,8 multiplied by 1.5 squared. So that gives me 11,03. Okay, so that is the distance from there. But then the distance or the height at C, we're going to get the 44, and then we subtract the 11,03. So we're saying 44 minus 11,03. So I'm ending up with a 32,97 meters above the ground. That is my answer. If there's anybody with a different answer, please just feel free to, to put it under the comment section so that that can be sorted out. All right, so that is that. Then 3.4, they want us that if after the first bounce, the ball reaches point C, sketch the position time graph. Okay, show the following, the time values at D and C, just in terms of T. Okay, not in the actual values. They want the heights of A and C. Okay, so what I'm going to do, what I'll do there, what's happening? So let's see, let's have our y-axis. That's our x. So this is going to be the position in meters. This is the time in seconds. So we had the 44 as the starting point. Okay. Then this thing is coming, and then it's going to bounce off to a point C. Okay. So if that is my point C, we know that the time for it to get to C is 3t, which means it's not going to make sense. Let me redraw it again, because the time is equal across. The time is just the same. Okay, so from here, saying that, and then it bounces off. So if this is what's happening? The graph is not graphing. Yo, what am I doing wrong? Okay, so let's see. Okay. So he's saying if this is 30, that is 60. So he's saying the height is just exactly the same. And I think that's what they wanted. They wanted this height above the ground. We said it is 32.97. Oh, Lord, what's going on? Okay, so that is what we would have done with the 32.97. And then this is our 44. I think that's all that they needed. All right, so that is for that last question, 3.4. Question number 4. Question number 4, they're telling us that a bullet, a wooden block of mass 150 grams, freely supported on brackets at the height of 2 meters. When the mass of this bullet is taken through, the bullet embeds itself in the block, and then the bullet block system rises vertically into the air for a few seconds, and then it comes back to the original position or place. So state the law of conservation of momentum in words. So we're saying that in an isolated system, the total linear momentum is conserved. Okay, then calculate the magnitude of velocity of the bullet block system after the bullet becomes embedded. So we know that momentum before is equal to momentum after. So this is going to be mass of the bullet, velocity of the bullet, plus mass of the block, velocity of the block, should give us the mass V final of the bullet. Since it's moving together, why not combine everything? So bullet plus mass of the block multiplied by the V final. So initially the block was at rest, the bullet was moving. So let me change these masses to kilograms. It's going to be 0.15 kilograms. Okay, so initially we say the bullet is going to be, the mass is 0.05 multiplied by 200. That's going to be a 0. It's going to be 0.2 multiplied by the V final. So 0.05 times 200, that's a 10, is equal to 0.2 V final. Divide both sides by 0.2. So our V final is 50 meters per second. Then 4.3 is the collision between the bullet and the block, elastic or inelastic, explained by using calculations to justify. So whether it's elastic or inelastic, we know that momentum will be conserved. So the only distinction between elastic and inelastic would be the kinetic energy. Okay. So let me look for the EK before and then the EK after. Okay. So I'll say that the EK before, my markers were U. There we go. So EK before is going to be a half multiplied by the mass of the bullet, velocity of the bullet squared, okay, plus mass of the block times velocity squared of the block. So since the velocity of the block is a 0, so I'll just focus on the bullet, okay? So that's a half times 0.05 multiplied by 200 squared, okay? So 0.5, 0.05 times 200 squared. That gives me 1,000. Is that true? This is 1,000 joules. Please just confirm. Just confirm. It's a half the mass of the bullet. Okay, and then the velocity squared. I think it's fine. Then let's look for the EK after. So it's going to be a half the combined mass, the bullet, and then the block times the V squared, which is the 50. So that's a half multiplied by 0.2 multiplied by 50 squared. Okay, so half times 0.2 times 50 squared. This gives me 250 joules. Now we can see that the energies are different. So we're gonna say that it's inelastic because there is no conservation. There is no conservation of EK or kinetic energy. Okay, or just say it's inelastic because kinetic energy is not conserved. Then 4.4, I'm saying 4.4 is on a different occasion, the bullet is fired closer to the wooden closer the wooden block at the same velocity and it exits a block with an upward velocity of this. So the bullet this time goes through. If the net force exerted by the block is this much, calculate the time taken. So we know that F net is equal to the change in momentum over delta T, or the rate in change in momentum. Okay, so that's net force. So what do they want? They want us to get the time. So delta T will be the change in momentum over the F net. Okay, so for us to get the change in momentum, I'll just use the same mass of the bullet, okay, and look at the different velocities. Can use V initial minus V final. Since the V, whichever one, any, can use any. Okay, I'm using this approach because I know that the final velocity is smaller. So, okay, over F net, so that's gonna be the 0.05 multiplied 2. That's gonna be 200 minus 195 divided by 5. Ne? When you subtract that, that's a 5, cancels 5, so it's gonna be 0.05 seconds. Okay. Question number 5, an ice skater of mass 53 kilograms moves on a frictionless surface AB, okay, with a velocity of 6 meters per second. So they start moving here at 6 meters per second. Then slides up the rough incline BC until coming to a stop. So the V final there is a 0. The height is 1.5 meters. State work energy theorem in words. So we know that the net work done total net work done is equal to the change in kinetic energy. Okay, so the net work done for an object is equal to the change in the kinetic energy. Then they want us to draw a laboratory body of all the forces acting on skate at point C for 3 months. So those are like 3 forces, 3 or more forces. Okay, so 1, since that is the stop, he's going to have his weight. Okay, the weight downwards. And then he's going to have his normal reaction. And then he's going to have the FG parallel. Sorry, my forces are curving. They should be straight lines. Okay, so that would be it. As much as it's rough, which means the friction is equal to the force that should be pushing him that side. So I'm not going to indicate it. Okay, then explain the term non-conservative force. So we know that is a force in which work done. Okay, it's a force in which the work done is dependent on the path that is taken. Okay, then they want us to calculate the angle theta, which is the slope skate experiences, a frictional force of 20 newtons while skating up. Okay, so if he's skating up, what will be the angle theta? So I looked at this question, and for 6 marks, there was a quicker approach for me that was giving me the same answers, probably what the examiner wanted in mind. Okay? So we shall start with, let's say, the long approach. The work net, W net, should be equal to, you can say, change in kinetic energy. Let me not say 0. We go again. There we go again. So I'm not going to call it a 0. Let me just say change in the EK. Okay, so we have work done that is from different forces, okay? We have the frictional force and then the FG parallel. So work done by the FG parallel plus the work done by the frictional force should be equal to the change in the EK. So I'm going to look at the point B, and I'm also going to focus on the point C. That's going to be a half M V final squared minus a half mv initial squared. Okay, so the work done by the gravitational force is going to be mass multiplied by the displacement, which is BC, plus the work done by the frictional force multiplied by the displacement BC should give me a half mvf squared minus a half mvi squared. So we know that the mass is 53 times 9,8, the sine of theta multiplied by BC, plus, remember we don't have theta, ne? Okay. Then the frictional force, they told us it's a 20 newtons. Okay, 20 multiplied by BC is equal to a half. The mass is 53. What is my V final? That is a 0 minus, I'll say 0 squared. I'm subtracting the V initial, which is 6 squared. Okay. But I know that sine of theta from this triangle, we can say that the sine is 1,5 over the hypotenuse. Okay, something like that. So it's 53 multiplied by 9,8 multiplied by 1,5 over BC times a BC plus 20 BC must give me Okay, so that's a half times that, square that. I get a negative answer, which I'm not interested in. Okay, I'm going to take the positive part of it and see I'm having 9. It's going to be 954. So this cancels. Then I have to transpose this to this other side. So 53 times 9,8 times 1,5 gives me 779,1 plus 20 BC is equal to 954. Let's move the 77 that side. Let's see if it will give us the answer we want. 954 minus 779.1, which gives me 174.9. Okay, 174.9, divide both sides by 20, which means my BC is gonna be 8.75 meters. Okay, so let me go back to the sine formula. We know that sine theta is equal to the opposite, is 1.5 divided by 8.75. Okay, to find the theta, it's gonna be the arc sine of this entire thing. Let's see. So 1.5 over 8.75. This gives me 9.87 degrees or 9.9 degrees. Okay, so that is what I'm getting for question 5.4. If there are any differences or variations, please feel free to. Okay, an observer with a detector that is standing on the side of the road records the frequency of a police siren that is moving in a straight line on 2 separate occasions. The police car moves at a constant speed on both occasions. The results are shown below, graph A and graph B. So in graph A, the recording was 1.1. Okay. And then in graph B, the recording was below the observed, which is 900. Okay, this is above and then that's below. So state Doppler effect in words. So we know that Doppler effect is the change. Okay. Is the change in the observed frequency. The change in the observed frequency. The observed frequency that is relative to the frequency of the sound source, because the sound source and the observer are moving in relative motion or in relative motion. Okay, then which graph AB shows the police car that is moving away? So if the police car is moving away, then the frequency must be low, which is graph B. Then we can say that the frequency is less than the observed. No, the observed frequency is less than the emitted frequency. So F0 is what is being emitted from the source. Then calculate the speed of the police car. We take 340 to be the sound speed. Okay, so what we're gonna do is gonna be more like a long question. Okay, so we know that Doppler. Let's go back to the formula. Doppler, where are you? There we go. So frequency of the listener is giving us that. Okay, so we're going to say that frequency of the listener is V plus minus frequency of the, velocity of the source and the frequency of the source. Now we have two scenarios, moving away and then moving towards, okay? And we have two different values. So let's, for moving towards, we have 1.1. Okay, so frequency of the listener is going to be 1.1. Is that making sense? Yes, it's below that. Okay, so 1.1 is equal to that velocity of the source, which is now velocity of sound in air, is 340. That's going to be a plus. Velocity of the listener, which is a 0, over 340 minus Vs multiplied by what I don't know. Okay, let's cross multiply. So 1.1 into 340 minus Vs is equal to, now let me divide. It gives me f of s. Okay, and then when it's moving away, it's going to be 900 is equal to 340 minus 0 over 340 plus VFS, no, Vs times Fs. Cross multiply, I'll have 900 into 340 plus Vs over 340 is equal to Fs. Let me equate the two equations. Okay, I'm saying we're equating the two equations. Okay, so what's going to happen? I'll have 1.1 into 340 minus Vs over 340 is equal to 900, 340 plus Vs over 340. So this cancels that. So 1.1 multiplied by 340, 374,000. We're subtracting 1.21 Vs is equal to 900 times 340, 306,000. Okay, plus 900, yes. Okay, I have to do the right thing, move the 306 that side, move the 1.1 that side. So when I subtract the 306, I'm getting 68,000 is equal to 2,000, yes. Divide both sides by 2,000. So this gives me just a 34 meters per second. So that becomes the velocity that the question wanted. The velocity of the speed car, or the speed of the speed car. Then 6.4, study the emission spectra A, B, and C of the distant stars observed on Earth. So which spectra B, and C indicates the star that is moving away? So for the star that is moving away, I'm going to go with option B, because you can see that these lines are moving towards the reddish side. And then 6.4.2, if the blue part of the spectrum is being observed from Earth, describe the frequency and the wavelength. So what we know is that the frequency for the blue wavelength is going to increase. Okay, the frequency increases, and what happens to the wavelength? And then the wavelength decreases, because we know that they are inversely proportional. All right, then question number 7. We have 2-point charges, A, B, that are placed 3 meters apart. The charge on A is 6 times 10 that, and then the charge of B is that. Then they are 1 meter apart, just as the drawing says. Then they want us to define what an electric field at a point is. So we're going to say that this is the force per unit charge that is experienced, per unit charge that is experienced by a positive, okay, a positive test charge that is placed at that point. Okay, then calculate the net electric field at P. So for us to get the electric field at P, the net one, we're going to look at the electric field at P as a result of A, and then the electric field at P as a result of B. So we're going to look at the two scenarios and then decide what we do next. Okay, so what I'm going to do then, and this is 7.2. Okay, so we're going to say that E is equal to KQ over R squared. So if I'm looking at AP, it's going to be 9 times 10 to the 9 times the charge of A is 6 times 10 to the negative 6. 6 times 10 to the negative 6 over the distance, which is going to be 4 squared, because it's already in meters. Okay, so when I punch this into the calculator, this gives me 3375. Okay, just to be on the safe side, 9 times 10 to the 9, multiplying by 6 times 10 to the negative 6. We're dividing it by that, 3375. Okay, then I look at the EBP. That's going to be 9 times 10 to the 9 times, that's a negative 3. So it's going to be a 3 times 10 to the negative 6 over 1 squared. Okay, so then what I'm getting here is going to be a 27,000. Okay, 27,000. So what is the formula for electric field? We know that it is F over Q, so it's Newton per Coulomb. Okay, and then the direction. So since it's a positive and a positive, there's going to be repulsion. So this one is acting, or it's being experienced to the right. And then this one, since it's negative and a positive, there's going to be attraction. And that's going to be to the left. So we're going to say that the E net is going to be the 27 minus 3375. Okay, 27,000 minus 3375, that gives me 23625 as my final answer, but this is going to be to the left. Okay, so that is the net electric field that was needed. Then 7.3, they're telling us if a proton is placed at P, calculate the magnitude of the initial acceleration of the proton if the mass of the proton is given as this. So we can use the F net. Okay, this is 7.3. We're saying F net is equal to MA. We're looking for the acceleration. But we know that E is equal to F over Q. So for us to get our force, we have to get the E multiplied by the Q. So E multiplied by the Q should give us the mass of the proton times the acceleration. Let me transpose and say it's EQ over the mass of the proton. So my net electric field is 23625 multiplied by the charge of the electron, not electron, proton. So we know that proton charge is just the same as the electron charge. It's just that the electron is negative and then the proton is positive. So that should be 1,6. Yeah, it should be 1,6 times 10 to the negative 19. So 1,6 times 10 to the negative 19. I'm dividing this by the mass. The question gave us the mass because electron and proton have different masses. The charges are just the same. So the mass they gave us is 1,67. Okay, so 1,67 times 10 to the negative 0.7. So when I punch that into the calculator, I'm going to end up with 2,26 times 10 to the 12 meters per second squared. So that will be the acceleration of that proton. Then 7.4, if an electron was placed at P instead of the proton, how would the acceleration compare? Now we know that acceleration is equal to, we said, F over m. So we know that acceleration is inversely proportional to the mass. Now, the mass of the electron, we saw that it was 1, so negative what? Was it negative 31? That's what I saw. 9,11 times 10 to the negative 31. Okay. 9,11 to the negative 31. Okay, so if this is 9,11 times 10 to the negative 31, so you can see that this negative 31 is smaller than the negative 27. Okay, now since the mass is smaller, then the acceleration is going to be bigger. So the acceleration is bigger, or it's greater since the electron has a smaller mass. And we know that acceleration is inversely proportional. So it's inversely proportional to the mass. So that would be the kind of explanation needed. Okay, question number 8. We have a battery, okay, with an unknown EMF and an internal resistance of 1 ohm connected to resistors, light bulb, and all of that. The 4 ohm is a bulb, and then 3 resistors, 2R, R, and then 6R. So define the term EMF. So EMF is basically the energy that we know that is electromotive force. So the amount of energy that is needed to move a charge, one electron charge, across the circuit. Then 8.2, when switch S is closed, the current through the ammeter is 0.2 amps. Write down the potential, and the potential difference across R1 is 6 volts across R1. So the voltage here is 6. Okay. Then they want us to get the voltage across V2 or R2. So we know that V is equal to IR. Okay. But then if this is 6V, the current is going to be the same. So let's kind of ignore the current. Is given as 2R. So which means every R represents a 3 volts. So the higher the resistance, the higher the voltage. The lower the resistance, the lower. So it's going to be a half, which I'm going to say it's just 3V. Would that make sense? Yes. Because this R1 is having the 6V. Yeah, it's 3V. Then what is the current that is passing through R2? So the current through R2, now I know that this is a 6V, this is a 3V, which gives me a 9V. If that is a 9V, same with this, it's going to be a 9V. But then the question wants to see, let's not look at the V's, let's look at the R's. So this is a 3R. This is a 6R. So there's more resistance here. Okay, and then there's less resistance here combined. So if this is 0.2, which means the current that is passing through here must be twice, which is going to be 0.4 amps. Okay, then they want us to calculate the resistance R3. Okay, so what I'm going to do, I'm going to look at the total voltage, which is 9V across. So we said the total voltage is going to be 9V for that and that. Then the current that is passing through the R3 is 0.2. Okay. So I'm going to say V is equal to IR. So 9 is equal to 0.2 multiplied by 6 R. Let me get just the individual resistor. If I can get the, because it's the same thing as me getting R3 when I say 6R. Okay. So that's going to be 1.2R is equal to 9. Divide both sides by 1.2. That gives me 7.5. This is what I'm getting. But now, since we're talking about 6R, but why did I even, because it would have made sense for me to just get a 45. Because 7.5 times 6 still a 45. So which means R3 is 45 ohms. Okay, so guys, I don't know. That is what I'm getting by just interpreting this. It can mean anything. It could be anything besides what I'm having. All right, then calculate the EMF. So we know that EMF is given as I into R plus small r. We said the current that is passing here was 0.4. So which means that the total current is 0.6. Okay. So I is 0.6. So we need to get the resistor, the effective resistance or the external resistance. So I combine this is going to be a 3R. Okay, then a 3R and 6R. That's going to be the product over the sum. So 6R times 3R divided by 6 and that's going to be 9R. I combine this, R cancels that. That's going to be 18, which gives me twice R. So 2 times, what was R? R was 7.5. So 2 times 7.5, that gives me 15 ohms. Plus the 4 ohms, we get the 19 ohms as the total resistance across. Then let's do the substitution and say that our EMF is going to be 0.6 into the 19 plus 1. So 0.6 multiplied by 20. That gives me 12 volts. So guys, that's what I'm getting for that question, 8.4. So the 6 marks, of course, you'll have to get the effective resistance here, the R external. That's where all the marks are. So 8.5 in a separate circuit, there's a variable resistor connected to battery with unknown potential difference as seen in the drawing. The graph below shows the relationship between the power dissipated in the resistor and the resistance. Okay. Use the graph to calculate the potential difference. So we're using power, okay? So with the formulas of power, we know it's IV. Since we're talking about resistance, let me use the one for the resistance. That's going to be I squared R. Does that make sense? Or we could have P is equal to V squared over R. Since we know that V is equal to IR, I is V over that. So we can use this. I think this would be the perfect combination to use. So let me try to get the gradient of this. So it's going to be the change in power over the change in 1 over R, which is going to give me the PR. And if I multiply this, I have a PR, which is V squared. Okay, so let's get the gradient. So change in Y over change in X, or change in power over change in that. So it's going to be 1000 divided by 10, which gives us 100. Ne? So which means our PR is 100. But we know that PR is given as V squared. So V squared is 100. Let's get the square root. So V is the voltage or the potential difference will be 10 volts. So that's how I would have gone about that. Question number 9. Study a diagram of a simple generator. Okay. Answer the questions that follow. Is this a DC or an AC generator? So one, I'll go with an AC generator. Reason, these rings are not split. Okay. Just made up of the brushes and blah, blah, blah. Then state the energy conversion that takes place in this generator. So we know that the generator converts mechanical energy, okay, to electrical energy. Mechanical energy to electrical energy. And then in which direction will then use current flow, A to B or B to A? So we have to use the right-hand rule, the generator. And the option that I'm getting is B2A if I use my right-hand rule, because we're going to have the force that side and then the field in that direction. So the current will be left to move in that direction, B2A. Then we have diagram that shows the EMF or one complete cycle. Calculate the resistance of the load if the IRMS is that. So this will represent the Vmax. Okay. So for us to get the VRMS, get the Vmax divided by square root of 2. But since we're looking for resistance, V is equal to IR. So resistance is just going to be VRMS divided by the IRMS. So 150 over square root of 2, that is giving me 106,066. Ne? So 106,066. I'm dividing it by 4,55. Okay. That gives me 23,31 ohms. The 9.5, that load is now replaced with a bulb that is having a power consumption of 400. And then in 3 minutes, they want us to get the energy. So energy is going to be power times time. Ne? So it's going to be 400 multiplied by the 3 minutes times the 60. So this gives me 72,000 joules or 72 kilojoules. Then the speed of the rotation of the coil is now doubled. Can we redraw? Now from grid 11, you know that induced EMF is directly proportional to the number of turns. So when you increase the turns, even the EMF will increase. So the graph should be starting from the same point, having the turning point at the same value, but then it should go up until double the value, then comes down and then drops to a double of the value. So this should be a 300, and then down here should be a negative 300. So in other words, the graph should be 2 times bigger. Then with what factor will the energy emitted change if the speed of the rotation is doubled or 2 times? So still, the energy or the EMF is directly proportional to the angular velocity of the coil. Okay, sometimes we can say EMF is directly proportional to the V. Now, if the V is doubled, it's moving 2 times faster. So the factor is going to be 2. Okay, and then the explanation for that, we can say that the induced EMF is directly proportional to the rate of rotation, the speed of rotation. Okay, so that is question 9. Then question 10, in an experiment, we have different light sources that are shown on the surface of some unknown metal. Then explain what work function is. So we know that work function is basically the minimum amount of energy. Minimum amount of energy that is needed or required to remove an electron. An electron from a metal surface. Okay. Then if electrons with maximum kinetic energy of this much are emitted from a metal surface with ultraviolet with this frequency, calculate the work function of the metal. So we know that E, okay, saying E should be the work function plus EK max. But our E is given as HF. This is going to be, what are we looking for? The work function, okay. And then EK max, okay. So our H is a constant, Planck's constant. which is 6.63 times 10 to the negative 34. Now the frequency of radiation we have is 6.3 times 10 to the 14. 6.3 times 10 to the 14 should give us W naught plus the energy they told us is 1.2 times 10 to the negative 19. So we just have to transpose this and move it that side. So when I do that with the subtraction, I'm ending up with 2.98 times 10 to the negative 19 joules. All right, so that is 10.2. Then 10.3, with the electromagnetic radiation with the frequency of this emit electrons from the metal surface. We choose a yes or a no, and then we support our answers. Okay, so we can start by one, calculating. This is 3 times 10 to the 16. Yeah? We're saying 3. The 3 times 10 to the 16. Now we can start by calculating the frequency of the work function. Okay, so from our formula page, I believe we have a formula like that. W naught. Where are we? E is equal to that, this and that. W naught is equal to H F naught. Beautiful. So I'm going to use this formula to calculate the initial frequency that I need, or the minimum frequency that I need. Okay. So the answer that we got here was 2.98 times 10 to the negative 19. So 2 times 2.98 times 10 to the negative 19 is equal to the Planck's constant multiplied by the frequency naught. Then let me divide both sides. Times 10 to the negative 34.63 times 10 to the negative 34. So this cancels that. So which means the minimum frequency required is going to be 2.98. That's negative 19. Dividing it by 6.63 times 10 to the negative 34. So this gives me 4.49 times 10 to the 14. Now, this is the minimum frequency that we require. Then the frequency that was given here is 3 times 10 to the 16. Okay, so we can see that this frequency is bigger than the threshold frequency. So therefore, answer is a yes. The radiation will do what? What was the question? Question was asking us, would the radiation be able to remove an electron? Will it emit electrons from the metal? The answer is yes, radiation will emit, since its frequency is greater than what we call the threshold frequency. So this is one way of doing it. The other alternative that I thought would make sense is if you look for the work function. Okay, the work function of this metal or this radiation, if we have to use the radiation the way it is. So just more like what we did in 10.2, we look for the work function with this sort of radiation and then see If the work function is smaller than that, then definitely it would have to emit the electrons. Okay, so that is what we would have done with 10.3. Then 10.4, when the photoelectric effect is demonstrated, a negatively charged plate is used. Okay, so if we are to use photoelectric, they are telling us that we have to use a negatively charged plate. Explain why, when this light, ultraviolet, is shown onto a positively charged, there's no charge that is lost. So what we can see is that, number one, we don't have electrons here that need to be emitted or need to be taken off. Okay, so we can say that we have no free electrons to be removed because they want the reasons why. Okay, and then number two, I don't know, it just rotates around, no electrons, no electrons. So you can say that a positively charged lacks electrons. And then we can say that ultraviolet or electrons can only be removed from a neutral surface, a surface that is neutral or negatively charged. But in this case, none of that applies. So these could be some of the reasons for 10.4. So guys, that's that. I'll stop there. And then I wish you guys all the best in your paper too. I sign out. Hello, welcome to this episode where we shall be looking at the proposed memorandum of the physical sciences, P.1, the Prelim of Gauteng. Okay, so we have 10 questions that we shall be looking at. So question number one, they're telling us if we have an air bubble in a tank that is rising vertically at a constant velocity. Okay, so if the velocity is constant, which means we don't have any sort of acceleration. So the forces acting are given below. So X, Z, and Y. So if the bubble is rising, which means this force, the upward force, must be greater than these two combined. Okay, so they're asking us for the incorrect option. Okay, so option A, they're telling us that X is equal to Y plus Z. Okay, there's some bit of truth in that statement. And then B, for us to get Z, we have to get X plus Y. No, there's no truth there because it should be a minus since these ones are acting in the opposite directions. Then for us to get Y, you shall get the X minus Z. That's okay. Telling us X is greater than Z. That's true, which is also greater than Y, which is also true. So since there is some bit of truth in A, we shall go with option B as our answer for the incorrect. Then if a person stands on a scale in a lift, the motion of the lift is given in terms of its acceleration, which situation represents weightlessness. And so we know that weightlessness is a scenario whereby an object or a person feels like a free body, where the only force that is acting on that object is the acceleration due to gravity. And we know that acceleration due to gravity will always act downwards, and the value is 9.8. So option A is off. Okay. We know that at a constant speed, the acceleration is a 0, but now the acceleration will always be 9.8 downwards. So I'm going to go with option C, whereby the acceleration, the downward acceleration will be 9.8 meters per second squared. Then 1.3, if a golf ball falls vertically downwards from rest in air and bounces back to the same height from which it was dropped. Okay, which of the following scenarios are correct? So the first option you have is it experiences a maximum speed at the minimum height. This is very true because for the object to get back to the same height, which means the speed at the point of bouncing should be greater. Okay, then the displacement falling is equal to its displacement that is rising, since the height reached before and after is the same, which means that option is also correct. And then it experiences minimum speed at the maximum height. So we know that at maximum height, the V final is always 0, which statement is also correct. So the combination of the options that are correct, I'm going to go with option D, which is all the 3. Okay, then 1.4, if a ball of mass m moving the velocity v collides head-on elastically. Okay, so elastically means we're going to conserve momentum and we're also going to conserve the kinetic energy. Okay, with another body of mass m moving at the same velocity v in the opposite direction, after collision, both bodies will move with the velocity v. That is true. Both bodies travel in opposite direction with a velocity v. This is a bit more detailed. The opposite direction and then a velocity v. I mean, it's a head-on collision. Okay, both bodies are going to go off with the same velocity. It's just more like they bump each other and then they move on in opposite directions. Okay, so both balls move at right angles. Nope, one ball comes off at rest and that's out. Okay, so I'm going to go with option B for 1.4 because it has more truth in it. And then 1.5, if a mass is lifted from rest in the ground to a point H, okay, P is the increase in the gravitational potential energy of the mass, and then K is the kinetic energy at mass H. Okay, the expression that is equal to the mechanical work done. So mechanical work is a combination of both the kinetic and then the gravitational potential. Okay, so which means I'll have my K and P added together. The combination with the plus, which is option A. We can't minus, we can't multiply. Okay, then what does the term redshift mean? 1.6. I'm going to go with option, an object in space, no? The color of a distance, somehow, the expansion of the universe. This makes more sense. Okay. Then 1.7, which of the following graphs has a slope that is equal to the Coulomb's constant? Okay, so we can see that the y-axis is having just the intensity, electric field. So if I'm to get the formula, which is E is equal to KQ divided by R squared. Okay, so if I make this the subject, if I make K the subject, it's going to be ER squared over Q, which could also be written as E over Q over R squared. That is our K. We know that it will be directly proportional. Okay, so all the graphs, like the shape is fine, but now what we need to check is basically the variables. So E over Q1, that is out. E against Q1 over R squared. This makes more sense. E over R squared, no. E Q over R, no. So C will make more sense. Then 1.8. 3 resistors are connected in a circuit. Then there is a 4th resistor that is connected parallel to the 4 ohm. Okay, so if we have another resistor that is connected in that format, if we had to compare the original circuit, compared to the original circuit, how will the power dissipated by the 8 ohm and the 4 ohm change? Okay, so initially, before we introduce this other resistor, the current that was flowing here, let's say, was maximum current. So 4 ohm was receiving the maximum current, and as much as the 8 ohm was getting split, okay, which was still a bigger share. Now, if we are to look at power, let's look at the formulas of power. We can use power is equal to IV, which is the same as I squared multiplied by R. Okay, so power is directly proportional to that, and okay. So if we introduce the 4 ohm resistor, what's going to happen is that the current that was initially in the circuit is going to be split up into 2. Okay, and then the fact that the current here is smaller than the original current, and we know that current is directly proportional to the power is going to decrease in the 4 ohm. Okay, so the same story happens to the 8 ohm and the 10 ohm, because this current that was split up must again be split up again for the second time, which means the power that is being received here is going to be way smaller. Okay, so even the power there is going to reduce as well. So decrease is option A that I'll go with. Then 1.9, an immersion heater can be operated either from an AC power supply or a DC. Graph represents the potential difference when the AC power supply is used. Okay. So if this is the AC, which means this is Vmax, okay, what DC supply? So which means we must get the VRMS, which is Vmax divided by the square root of 2. So our Vmax is 12, so 12 over root 2. That would be the answer. Then 1.10, the work function of a metal is given as that. Then if this metal is illuminated with light of frequency 3F0,